Hi everyone, in this video we are going to discuss the 4 major units of radiation. And so we usually discuss these in 2 different categories, so I'm going to stick with that method because I think it's easiest to understand. So the first one, which is the oldest or the original unit of radiation, is called REM. It's R-E-M. But that's the old one, that's the antiquated term. Most people don't use that anymore. Most people, especially internationally, use the term sievert. And that's usually written by a capital S and a lowercase v. And so we know that 1 sievert is equal to 100 rem. And like I said, you can use the unit rem if you want, but I would highly encourage you to try to become more comfortable with sievert just because that's the more common one. The last unit we're going to talk about is rad, R-A-D, and that stands for your radiation absorbed dose. And this is more of a localized term. Excuse me, I'm bubbling in my throat. I have a localized term. And so when we talk about rad, what we usually are saying is that there is the energy that is deposited in tissue. And like I said, this is your localized term. So 1 rad, R-A-D, is equal to 0.01 joules of energy per 1 kilogram of tissue. This is your localized term. Personally, I think this is the most useful definition because it takes us back to joules and it gives us a unit that we're more familiar with. But if we had to pick out of these 3, sievert or rad are the 2 most important ones. So let's do a quick practice problem here to see if we can remember how to do some dimensional analysis. So, how many rads does a 100 kilogram person receive if they absorb 0.5 joules of energy? Go. All right, did you get an answer? Hopefully you did, but if you didn't, that's okay. I actually thought this was a semi-tricky problem because it's a little bit different approach than we usually do for dimensional analysis. So personally, how I would have accomplished this problem is I would start it off by saying, I know that a 100 kilogram person received 0.5 joules of energy through radiation. And so then what I would do is I'd come up here to our little conversion that we had earlier, saying that 1 rad is equal to 0.01 joules of energy per every 1 kilogram of tissue. So then if you put this in your calculator properly, you should see that this person, this 100 kilogram person, actually received 2 radiation absorbed doses into their body. So now, what does that actually mean? We know they got hit with radiation, but what does that mean? And the biggest thing I can tell you is that all radiation is not equal. Okay, it's very, very different and entirely depends on a couple different sources. The first thing is, what is the source, right? Where are you actually getting this source of radiation from? And based on your location and your lifestyle, your source of radiation or your annual dose of radiation is going to be very, very different from your neighbor or for someone who lives in Florida or maybe Texas or maybe somewhere else. And especially if you're someone who's outside a lot or maybe you smoke a lot or maybe you're in hospitals a lot, your dose, your annual dose is going to be very, very different from somebody else. So your lifestyle and your location are your 2 biggest factors. So let's break it down here. And so what I want to do is look at a table of annual radiation dosages. And so what I have on the left side are just sources of radiation, and the right side are your microsieverts per year. So this is an annual dosage. So for this random person, the sample person, they're saying that they're around the sea, so they get some radiation from the sea. They're saying they get some from the building materials, some rocks and soil. They see that they're getting radiation from food and water, also fallout and nuclear weapons testing. Then we see our medical procedures right here, where we see chest x-ray. So basically for this person, all they have are dental x-rays, so not bad, not much. This person doesn't travel too much. If you travel a lot, so if you're a businessman or woman and you're flying all the time, your radiation exposure is actually significantly higher because there's a lot more radiation higher up, right, when it's closer to other planets and other forms of radiation. And there's also several other pieces. Do you live near a nuclear plant? Do you live near a power plant? Do you smoke? Do you watch a lot of TV? Are you using a computer terminal? So on and so forth. And so it really just depends on your lifestyle. But the one thing I want to point out was the number 6, your medical and dental x-rays, all right? So for this person, this human, we're talking about a relatively healthy human. However, what we can look at here is we can see that based on your lifestyle or based on your original health, your amount of radiation for medical procedures is completely varying. So we can see that this is again in REM now, so an older unit here, that for dental x-rays, you barely get any REM, so millirem, right? You're at 0, okay? And then, or you have millisieverts at the bottom. It depends on which unit you're looking at. Chest x-ray, not very much. Mammogram, not very much, which is good because women need to do mammograms all the time to make sure that they're not sitting there waiting for breast cancer, okay? So you need to be careful, get screened. Your lumbar spine x-ray, not very much. As soon as we start talking about CT scans, that's when doctors and scientists start freaking out. CT scans are really bad for you. You get a lot of radiation when you get a CT scan. Surprisingly, if you had to pick, you would probably prefer to get a CT scan of your head than your chest. The last thing you want to do is get a CT scan of your abdomen. So like I said before, be cognizant of this. You need to be your own best advocate. If you go to a hospital and they're like, we want to do a CT scan of your head, your chest, and your abdomen, you go, hold up, bro. Let's have a conversation about this first. Is that important? Is this necessary? Do not let somebody just do scans of you randomly. So let me ask you, if you had a chance, would you prefer, I should say choice, not chance. Would you prefer a dental x-ray or a CT scan? Hard question, right? Go. All right, did you get an answer? Hopefully you did because I just said it. If you had to pick one, you definitely 100% want a dental x-ray. You absolutely want to avoid CT scans if you have any choice whatsoever. All right, so now up until this point, we've discussed 3 different units. We discussed REM, sievert, and rad. But now what we're going to do is talk about the 4th unit. The first 3 usually we talk about in terms of annual doses or large doses. This last one is called a curie, and we use a curie to discuss the radioactivity of a specific sample. So let's write this out. A curie, named after Marie Curie, right, is represented by a Ci. So 1 curie is equal to 3.7 times 10 to the 10th disintegrations per unit time, but it's not per any unit time, it's actually per second. They're very specific about this. So now what's a disintegration? Disintegration is basically a particle that's released. So specifically though, an alpha, beta, or a gamma particle that is released, and then we measure this for a curie in the unit per time of a second, okay? So 1 curie is equal to 3.7 times 10 to the 10th disintegrations per second. And just so you know where this number came from, that's the amount of radiation that is released from 1 gram of radium, okay, so which is something that Madame Curie actually studied a lot. So now, frame of reference, 100 to 200 million curies of radiation was released into the atmosphere during the explosion that occurred in Chernobyl. That is terrible, absolutely terrible. And again, just for a frame of reference of that, that was about 2 times as much radiation that was exposed in the atomic bombs that we dropped in Nagasaki and Hiroshima, okay? It was terrible. Chernobyl was a really, really bad accident, and those amazing, brave, just absolutely brave first responders that ran into the building when everybody else was running out, they were immediately basically sacrifice themselves for the greater good of the society. So hats off to first responders and firefighters and first med and anybody who ever has anything to do with first responding. We're going to end this video with that. Thank you so much for your service, and we're really grateful for it. Drink water, guys.